Hi, my name is Junrui. I'm a PhD student from UC Santa Barbara. Today I will be presenting our paper, Certifying Zero-Knowledge Circuits with Refinement Types. This is a joint work with the wonderful people from UT Austin, Simon Fraser University, Veritas Axiom, and Polychain Capital. So in a zero-knowledge proof, there's a prover who is trying to convince the verifier that the result of some computation f given input x is y, and the prover can convince the verifier without revealing what the input x is. So thanks to this privacy-preserving property, zero-knowledge proofs are becoming the enabling technology behind a wide range of applications, from anonymous voting to privacy in blockchain. However, the intended computation f usually cannot be expressed as a normal program. Instead, the same computation needs to be encoded in some way as an arithmetic circuit, which are systems of polynomial constraints over finite fields. Because of the difference between these two computation models, a natural question arises. Do the intended computations align with the arithmetic circuits? If that's indeed the case, then we say that the circuit is functionally correct. It turns out that for zero-knowledge proofs programs, ensuring functional correctness is both extremely critical and it can be hard compared to other domains. It is critical because for functionally incorrect circuits, the prover may be able to carefully construct secret inputs to make the overall circuit come out to be true. However, even with this exploit going on, the verifier may not even notice because of the zero-knowledgeness. The secret inputs maliciously constructed by the prover may be hidden. So, due to the zero-knowledge property, the verifier cannot just observe the state of the system and somehow detect that something is going wrong. Despite the critical importance of functional correctness of ZK circuits, ensuring it can be extremely hard because developers often need to express the intended computation in a low-level language in order to gain the maximum amount of performance. For example, for this simple integer comparison, this is how one would encode in a arithmetic circuit using the Circom language, which is one of the most popular ZK programming languages. As you can see, even a simple computation can lead to a very complex circuit, and in fact, this circuit contains a tiny bug, which means that using this bug, the prover can make malicious exploits, and any library that even transitively depends on this circuit may be silently exploited as well. So due to the critical importance of functional correctness, in this work, we try to apply formal verification to ZK circuits to make the verification of functional correctness as easy as possible. At the center of our work is a language called CODA, which is a verification-friendly, domain-specific language for programming ZK circuits. The key features of CODA are threefold. First, it allows the developers to concisely specify what it means for the circuit to be functionally correct using what we call refinement types. Second, CODA provides a high level of assurance using machine-checked proofs. And finally, it facilitates the proving process through a combination of interactive proving and automation. So here is the typical workflow of using CODA. First, the developer would express the intended computation in a high-level circuit using the CODA language. Then, the developer would also provide a specification of the functional correctness of the circuit in the form of refinement type annotations. Then the CODA type checker reduces the problem of ensuring the circuit satisfies its functional correctness through a combination of automatic type checking as well as what we call proof obligations, which correspond to properties that the type checker cannot automatically establish. Then the developer can interactively discharge those obligations through interactive proofs. And finally, if all of the obligations can be proven, then Coda guarantees that the overall circuit is correct, and it can compile the circuit into various back-end constraint systems such as R1C has. Now I will give a very quick example to illustrate this workflow. On the left is the same circuit that we just saw, which expresses the less than computation, and on the right is the same circuit encoded in Coda. The key is that with this high-level language, the developer can more concisely express the intended computation, which closely resembles normal programming. What is more important is that the developer can now concisely specify the functional correctness of the circuit using refinement types. Basically, refinement types are a form of contract which the circuit must satisfy. For example, here, the refinement types specify the contract that, assuming the inputs A and B are binary arrays of field elements, then the return of the circuit must also be a binary field element that indicates whether A is less than B as big integers. Then this refinement type contract is consumed by the type checker, which breaks down the circuit and its complex specification into a set of small independent verification tasks called proof obligations. These obligations are encoded into an interactive theorem prover called COG, so that the developer can incrementally build up the proof to discharge those dilemmas. However, one key challenge in the ZK domain is almost all the dilemmas will invariably rely on some properties of the finite fields, which in theory is very hard to automatically reason about. So to make the interactive proofs as easy as possible, Coda also provides a set of reusable tactics to reduce the burden of writing manual proofs. So through either automatically discharged proofs or semi-automated proofs, Coda will be able to verify the overall correctness of the circuit. Using the same kind of development workflow, we have used Coda to verify 77 real-world ZK circuits from popular libraries. And throughout the process, we have actually discovered 6 previously unknown functional correctness bugs. So someone may have been exploiting those bugs without us knowing it. We also patched those circuits so that they can be fully verified, and our pull requests have been merged into some of the repos. So this is Coda, a tool for formally verifying ZK circuits. Coda is open source, and you can click on the GitHub link here or scan the QR code to view the source code, the circuits, and their formal verification proofs. With that, I would like to conclude my talk.